In previous video, we learned that cardinality of natural numbers, whole numbers, integers and rational numbers is same, and it is represented by a special symbol aleph naught. Today, we will see that cardinality of real number and any interval on real number is also same, and that is represented by a special symbol continuum. Also, we will see a relation between continuum and aleph naught, which is 2 raised to the power aleph naught equals to continuum. So let us first see why the cardinality of minus 1 comma 1 is same as the cardinality of set of real numbers. Okay. So cardinality of two sets is the same if we can define a 1 onto function between them. So if we can define a 1 onto function between minus 1 comma 1 to r, then cardinality of both of these will be equal. Okay, so let us define a function. Let us say fx is equals to tan pi x by 2. You can see that this is a 1 onto function from minus 1 comma 1 to real numbers, and that is why cardinality of minus 1 comma 1 is same as the cardinality of real numbers. Similarly, let us define a function from 0 comma 1 to real numbers, which is 1 onto, and in this way we will see that cardinality of 0 comma 1 is same as real numbers. So let us define it as hx is equals to tan pi times x minus 1 by 2. So this is also 1 onto function from 0 comma 1 to real numbers, and you can see that cardinality of 0 comma 1 is same as the cardinality of real numbers. Okay, nice. Okay, so let's move forward. So we can define sets on the basis of cardinalities as finite sets and infinite sets. Finite sets have finite number of elements like 0 element, 2 elements, 3 elements, 100 elements, and so on. And infinite sets have infinite number of elements like natural numbers, rational numbers, real numbers, etc. Now, here are two types of sets also called countable and uncountable. So if the cardinality of a set is less than or equal to aleph naught, then the set is countable. Here also we have two type of countable sets, countable finite and countable infinite. Both are countable. Okay. So countable infinite are like natural numbers, whole numbers, integers, and rational numbers which are infinite but their cardinality is same as natural numbers. And uncountable sets are like real numbers 0 comma 1, power set of real numbers, right? Here 0 comma 1 is the interval. I think it is clear. So their cardinalities is more than aleph naught. It is not necessary that their cardinality is equal to continuum. It can be more than continuum also, but if it is more than aleph naught, then it is uncountable. Now let's proceed. So let us first see property of aleph naught. Let us see what is the value of aleph naught times aleph naught. You might be thinking it is aleph naught square, but not exactly. Let us see. So aleph naught times aleph naught is equals to cardinality of natural numbers times cardinality of natural numbers, right? Which is equals to the cardinality of Cartesian product of natural number with natural numbers, right? Set of natural numbers with set of natural numbers. Now set of natural numbers cross set of natural numbers means all the ordered pairs a comma b where a and b are natural numbers, right? So first one should be a natural number, second one should be a natural number, and in this way all the possible ordered pairs which can be formed belong to this set, which is 0 comma 1, 1 comma 0, 0 comma 1, 2 comma 0, 1 comma 1, 0 comma 2, and in this way let us list all the ordered pairs, right? Now let's number them. So let us number them diagonally, like say it is 1, then it is 2, it is 3. Okay, move diagonally like this. Then it is 4, 5, 6. Then 7, 8, 9, and some element must be here, so it is 10. And again 11, 12, and so on. So you can see that we can define a 1 1 onto map from natural numbers to n cross n, right? This is 1 1 onto, and therefore their cardinality is same, right? So aleph naught square is again equals to aleph naught. Interesting, right? Okay, now since aleph naught times aleph naught, it is equals to how much? It is equal to aleph naught square. So if and aleph naught square is again equal to aleph naught, so if we multiply it again with the aleph naught, then aleph naught times aleph naught and aleph naught is again equal to aleph naught, right? So in this way, if we multiply this aleph naught with itself finite number of times, then it is again equal to aleph naught. But we will see that if we multiply it aleph naught number of times, it is not equal to aleph naught. Now we are interested in proving the relation that 2 raised to the power aleph naught is equals to continuum and y. So let us move towards the proof. So here we know that every real number has a binary representation, no matter the number is a recurring decimal or terminating decimal, or it is non-terminating, non-recurring, irrational, etc. All the real numbers have a binary representation. Now we will use this binary representation to construct a function. Let us see how. We will number the places of this binary number. We will number the place before decimal as 0, and before it -1, -2, -3, -4, and so on. And after decimal we will number them as 1, 2, 3, 4, and so on. Now using them we will construct a function from natural numbers to 0, 1. So let us see. Since 0 is below 0, so we will define f0 as 0. Since under -1 it is 1, so we will define -1 is equals to 1. Similarly, since it under 4 it is 0, so f of 4 is equals to how much? F of 4 equals to 0. In this way, if someone asks the value of f of -3, so f of -3, how much? Under -3 we have 1, so f of -3 equal to 1. In this way we can tell all the values of the function, right? Now nice. So this binary representation is giving us a function from natural numbers to 0, 1. Okay, so another binary number will give us another function. Let us number them as 0, -1, -2, 1, 2, etc. So here value of f0 is equals to 1. You can see value of f1 is equals to 1 because under 1 we have 1, under 2 we have 1, so f of 2 equals to how much? 1, right? F of 3 is 0, f of -2 is 1, f of -1 is 0, etc. Now I think it is clear that we, for every binary number, we can construct a function. Okay, in the similar way, if we have a function from integers to 0, 1, I'm sorry, I was speaking natural numbers, but we are defining a function from integers to 0, 1. So if we have a function from integers to 0, 1, we can make a binary number with the help of this, right? Suppose here 0 is connected to 0, so on the place 0 means before decimal we have 0. Since -1 is connected to -1, you can 1, you can see, so under -1 we have 1. Okay, so in this way every function will give us one binary number, one binary representation, and every binary representation gives us one function. So one function means one real number, and one real number means one function. Okay, nice. Now let us see the total number of possible functions from integers to 0, 1. So here to define a function we have two choices for 0. We can connect 0 to 0 or 0 to 1. So it has two choices. Similarly, -1 has two choices. It can be connected to 0 or 1. So let us multiply 2 for it. Similarly, 1 has two choices, right? So again multiply it with 2, and in this way every integer has two choices. So we have to multiply 2 with itself how many times? Aleph naught number of times, right? So it is equals to 2 raised to the power aleph naught. And how many functions are here? We know that every function represents a real number and every real number represents one function. So total number of functions is same as the total number of real numbers, which is equals to continuum. So this was what we were trying to prove, and we have proved it, that 2 raised to the power aleph naught is equals to continuum. Interesting, right? So if 2 raised to the power aleph naught is continuum, then let us see what is the value of 3 raised to the power aleph naught. So as we were using binary representations, we can use ternary representations also for the real numbers, right? And for every ternary representation we have a function, and for every function we have a ternary representation, right? So using these representations we can construct function, and we will find that 3 raised to the power aleph naught is also equals to continuum. In this way 4, 5 and so on raised to the power aleph naught is equals to continuum. Let us see what is the value of aleph naught raised to the power aleph naught. So since we know that 2 is less than aleph naught and aleph naught is less than continuum, right? Now C can be written as 2 raised to the power aleph naught. We have just proved it. Now raise all these to the power aleph naught. So what we get, 2 raised to the power aleph naught is less than or equal to aleph naught raised to the power aleph naught, which is less than equal to 2 raised to the power aleph naught times aleph naught. And here aleph naught times aleph naught is again equals to aleph naught, right? We have also seen this. So 2 raised to the power aleph naught is less than equal to something which is less than equal to 2 raised to the power aleph naught, means this middle term aleph naught raised to the power aleph naught is also equals to 2 raised to the power aleph naught, which is equals to C. So here we get its value is also equals to continuum. Interesting. So this was all for today. Don't forget to like and share our video, and for more such videos subscribe to our channel Brain Exploders. Thanks for watching.